Good evening, all. Myself, Pratik. I'm going to present the literature survey for the course self-driving cars. I have chosen the base paper as PedAST-GCN, Fast Pedestrian Crossing Intention Prediction using Spatial Temporal Attention Graph Convolution Network. This is the base paper. Overview of this base paper is this is a lightweight and efficient model designed to predict pedestrian crossing intention in real time for autonomous driving vehicles. It uses a spatio-temporal attention graph, a graph convolution network to model pedestrian body key points over time, capturing both spatial relationship and the temporal dynamics. The attention mechanism helps the model focus on the more relevant features, improving accuracy and interpretability. This uses JAV and PA datasets. This outforms existing methods in both speed and prediction accuracy, make it highly suitable for real-world autonomous system application. Objective of this paper is to create a fast and reliable system that can predict if a pedestrian is about to cross the road, and to use graph-based learning that understands how a person moves over time by looking at the body key points. Next, to make the model smarter by adding attention, so it focuses on the most important moments and patterns. To ensure the system works quickly and accurately, even with just a few frames observation, allowing vehicle to react early and safely. Methodology: post extraction. Pedestrian body key points like head, shoulders, and legs are extracted from the video frames using a post extraction model. These key points capture the pedestrian's posture and movement over time. Second, graph construction. A spatio-temporal graph is built using key points, where nodes represent joints and edges capture spatial within the frame and temporal across frame relationship. This helps model both body and structural motion. Next, ASC graphical convolution processing and with attention. The graph is processed using spatio-temporal attention graph convolution network. This network learns movement patterns and uses intention to focus on the most relevant joints and frames. Next, intention prediction. Based on the learned features, the model predicts whether the pedestrian intend to cross the road or not. It is designed to be fast and accurate, making it ideal for real-world applications. Limitations of the paper: limited performance in low visibility conditions, next sensitive to occlusion, dependence on post quality, and data set specific tuning. Next, this is my reference paper one, which title is Predicting Pedestrian Crossing Intention in Autonomous Vehicle. The overviews of this paper is the paper focused on improving the safety and decision making of autonomous vehicle by accurately predicting whether pedestrians intend to cross the road or not. It proposed a two-stream model that leverages spatial and temporal features through the combination of CNN and a long LSTM network. This model tested on a real-world data sets like JAV and PAV, showing superior performance over existing methods. Objective of this paper is to predict crossing intention of pedestrian using only video inputs. Develop a model that works efficiently in real-time scenarios with high prediction accuracy, and improve safety and planning capabilities of autonomous driving systems through early intention detection. Methodology: spatial features extraction. Each pedestrian frame is cropped and passed through a resonate 50 to extract visual features like postures and orientation. Next, temporal modeling. The sequence of speech is then fed into LSTM network, which captures motion pattern over time. Example: walking, direction, or speed, or motion. Next, prediction layer. The LSTM output goes through a fully connected layer with softmax to classify whether the pedestrian intend to cross or not. Next, dataset use. The model is trained using a GAD and PAS. Limitations of this paper are of only visual input used. Like it uses only a video and it's not applicable in real world application, like a real time application. Limited long term prediction. This suited for a short video, short time window, like 1 to 2 seconds. And performance drop in accuracy can decrease when pedestrians are partially hidden or objects or other people. Like no multimodal integration. It doesn't use additional sensory inputs like cameras, like lidars or radars. Use only cameras. Next is my reference paper two, which is titled is pedestrian trajectory, trajectory prediction with CNN. And summary of this paper is this paper proposed a novel approach of predicting pedestrian trajectories using convolutional neural network instead of the more commonly used recurrent neural networks. The author argued that CNN can effectively capture spatial temporal dependence in sequential data while offering advantage in computational efficiency. Objective of this paper is to investigate whether CNN can serve as a viable alternative to RNN or not. Like next, to design a lightweight and efficient CNN based model that accurately forecasts pedestrian paths. Next, we compare the performance of CNN with state-of-the-art methods to establish benchmarks. Methodology of this paper is input representation. This model takes as an input of a sequence of 2D coordinates representing a pedestrian path trajectory. It's convolution architecture. This model used 1D temporal convolution instead of recurrent layers. A series of static convolution layers are applied to the input sequence to capture spatial temporal pattern motion. As more layers are added, the network receptor clearly grows, enabling it to learn from longer sequences. Output, the fine convolution outputs are predicted of future XY question, typically for next 12 times. This forms the estimated future trajectory of the prediction. Next, training and optimization. Trained using mean squared error loss on ETH and UCY datasets. Limitations of this paper, it does not model interaction between multiple systems. It ignores scene context like roads, obstacles, or traffic signals. Works with fixed length inputs and outputs, limiting adaptability. May underperform in complex and crowded real world settings. Now, this is my reference paper 3. Type is pedestrian detection using dense connected block and attention modules. Overview of this paper proposed a DA-net, like a dense connected block attention modules, a pedestrian detection frame that integrates dense and attention modules to enhance feature extraction and focus on important spatial details. DA-net improves the detection accuracy by leveraging rich features refused from DCBs and selectively emphasizing pedestrian relevant regions through attention mechanism. It outperforms traditional CNN in both accuracy, robustness, and especially in complex scenes. Objective of this paper is to improve pedestrian detection accuracy in challenging scenarios like varying scales. mm, Next, to enhance feature representation using dense connected blocks for better information flow. Next, to apply attention mechanism to focus the model on pedestrian relevant area to reduce false positive and boost performance on benchmark pedestrian dataset. For methodology, input and backbone network. The model takes an input image and processes it through a backbone CNN, enhanced with dense connected blocks. DCBs allows features, reuse, and stronger grading flow by connecting each layer to every other layer in a block. Attention modules. Attention modules are introduced to guide the network to focus on informative spatial regions and suppress irrelevant backgrounds. Feature efficient. Feature extracted from different layers are combined to maintain both low-level picture details and high-level semantic information. Detection head. Finding detection head generation, bounding boxes, and confidence score of pedestrians. This model is trained using a standard object detection was common classification and localization objects. Limitation of this paper are this may still struggle with extremely small or heavy occluded pedestrian. Computational complexity is higher and requires sustainable training on data for optimal performance. Perform may vary across different weather or lighting conditions, not covered in time. And this is my paper for the topic is deformable spatial temporal convolution neural network for pedestrian traffic reproduction. This paper introduced DST convolution neural network, a novel deep learning framework for pedestrian traffic prediction that uses deformable spatial temporal convolution. Unlike standard CNNs, this can dynamically adjust its receptive fields based on pedestrian movement, capturing both spatial and temporal dependencies more efficiently. This model aims to improve pedestrian accuracy in complex environments with irregular motion pattern and varying pedestrian behavior. Objective of this paper is to improve trajectory prediction accuracy by modeling complex spatial temporal dependencies to introduce deformable convolution that adapt to irregular pedestrian motion to address limitation to traditional CNN or trajectory modeling and to achieve a better generalization in real-world pedestrian tasks. Its methodology. Input representation. The model takes an input as sequence of past pedestrian positions. Example like 8 time steps of XY coordinates and etc. Deformable temporal convolution. Temporal convolutions are adapted using deformable kernels, which allows the model to learn flexible sample location in time capturing diverse motion patterns. Deformable spatial convolution. Spatial convolutions are also made deformable to adjust the spatial receptive field dynamically, improving the model ability to follow pedestrian path accurately. Prediction and train. The output is predicted sequence of a future XY position. The model trained using mean square error between predicted and actual trajectories on standard errors. Limitations are higher computational cost. does not explicitly model pedestrian to pedestrian interaction, may require careful tuning to balance flexibility and overfitting. Limited integration of environmental or scene context information. And next, reference paper 5, the is learning pixel level and instance level context aware features for pedestrian detection in crowds. This paper proposes a pedestrian detection framework that jointly learns pixel level and instance level context aware features to improve detection performance in crowd environment. By combining semantic segmentation with object detection, the model enhances its understanding of both local and global context, enabling it to better distinguish pedestrians from the background and from each other in dense scenario. Objective is to improve pedestrian detection accuracy, especially in crowded and occurred scenes. To jointly train detection and segmentation tasks for richer context representation. Next, to reduce false positive and missed detection in challenging real world scenarios. Next, to extract both pixel level and instant level features. Methodology. Input and backbone network. The model processes input image using a scene and backbone that extract deep features shared across two parallel branches, one for detection and one for segmentation. Pixel level context modeling uses a semantic segmentation branch to generate pixel-wise pedestrian labeling. This helps the model understanding pedestrian shape and boundaries, especially in urban areas. Instance level context modeling applies both direction to generate bounding boxes and classify pedestrian using instant level features. Joint training strategy. The network is trained end to end using combined laws that include detection laws and segmentation laws, allowing both branches to complement each other. Limitations performance may degrade in poor lighting and weather conditions, requires more computational and memory due to branch architect, needs carefully annotated segmentation and detection data, may still struggle with extremely dense crowd or overlapping pedestrians. This reference paper says that it is bed joint net, a joint head, shoulder, and full body deep network for pedestrian detection. This paper introduced bed joint net, a deep neural network that jointly detects the head, shoulder, and full body region of pedestrian to enhance detection performance. By learning correlations between these two regions, the model can detect pedestrian more accurately, especially in case of truncation or unusual forces. This joint detection approach helps in recognizing pedestrians when parts of the body are missing or obscured. The objective of this paper is to improve pedestrian detection accuracy by leveraging both full body and head shoulder features. Next, to handle occlusion and partial visibility more effectively. Next, to build a network that shares features and jointly learns to detection tasks to outperform traditional full body only detection method in complex urban scenarios. And on this methodology, a shared backbone feature extractor. The network uses a shared scene and backbone to extract base feature from the input image. A dual branch detection. This feature are passed into two branches. One is head shoulder detection branch, and another one is full body detection branch. Joint learning. The model is trained to jointly optimize both detection tasks. Shared features allow the head shoulder branch to assist the full body branch. Visibility is low. Post processing intuition. Detection result from both branches are used using confidence scores and overlap threshold to find less accurate prediction. Limitations of this paper. This may struggle with extremely small scale predictions or distant views. Increased computation cost due to dual branch architecture. Requires well annotated head, shoulder, and full body ground. For time. Detection can still fail under extreme occlusion or unusual forces, not well represented in training data. This is my reference paper sound titles pedestrian detection method based on FCOS DFT model. This paper represents the pedestrian detection method based on the fully convolutional one-stage framework enhanced with a deformable enhanced feature pyramid network. Unlike anchor-based detector, this treats detection as per pixel prediction task, eliminating the need for predefined anchor boxes. By integrating deformable enhanced features pyramid network, the model adapts more effectively to various pedestrian scales and shapes, improving detection accuracy, especially in complex environments. The objective of this paper is to build an anchor-free pedestrian detection using a FCOS framework. To enhance multi-scale features learning using a DEFTN module to improve adaptability to different pedestrian size posts and occurrences, to reduce false detection while maintaining high recall methodology. FCOS platform. The model uses FCOS architecture which performs object detection directly from featuring maps with answer box predicting bounding boxes at every pixel location. A deformable enhanced JFTM integrates a deformable convolution into a feature family network to make future extraction more flexible and responsive to pedestrian shape and orientation. Future fusion and detection. Features from multiple scales are used for robust detection of pedestrians across space. The model predicts class, center mass, and bounding mass coordinates at each pixel. Training and evaluation. The model is trained on standard pedestrian dataset using a combination of classification and regression loss. Evaluation shows improvements over traditional anchor-based and basic SEO methods. Limitations of this paper are a deformable layer and computational overhead. Next, performance depends heavily on the quality of the feature parameter. It may still struggle with a dense operation crowded since not explicitly designed to incorporate semantic or contextual information. And this is the tabulation column compared in all the 8 papers, including my base paper. Um, yeah, every paper uses camera sensor model, um, and I have mentioned the data set used and performance limitations. Okay, now I'll explain why I would choose on this paper as base paper. Number one, superior is a spatio-temporal modeling. PedAST-GCN effectively combines graph convolution network with temporal attention to model both spatial interaction between pedestrian and temporal movement patterns. Most other approaches either focus only on spatial, like only CNN or RNN, or only temporal aspects like LSTM based, limiting their effectiveness in dynamic and interactive environment. Second thing is real-time performance with lightweight design. With an inference time of just 5.5 milliseconds, the model is optimized for real-time use in autonomous vehicles. Unlike other methods that rely on heavy computation and large sequence model, PedAST-GCN maintains high accuracy without compromising speed, making it ideal for deployment on embedded systems and autonomous navigation vehicles. Effectively, and third one, effective multi-agent interaction understanding. The graph-based framework allows the model to naturally capture interaction between multiple pedestrians, which is essential for predicting intentions at busy intersections or crosswalks. In contrast, many existing models treat each pedestrian differently, missing out the social dynamics. For strong generalizability across the real-world scenarios, tested on a diverse real-world data sets such as PIE and JAD. This paper demonstrates a more reliable performance across varying various lighting conditions and weather conditions on crowded scenarios. Other models are often evaluated on simpler data sets like ETH or UCD, which don't reflect the full complexity of real-time environments. Next, interpretable and modular architecture. The module's attention-based graph layer provides insights into which pedestrians and timestamps influence predictions, aiding in system transparency and debugging. This is a major advantage over a CNN or RNN model, which often acts as a black box. Conclusion: I choose PedAST-GCN this paper because it offers a balanced blend of high accuracy, real-time performance, strong generalizability, and interpretability. Compared to other models reviewed, it addresses key challenges in pedestrian intention and prediction more effectively, making it solid foundation for further research and development. And these are the limitations and solutions to how to overcome this. First one, limited environmental adaptability. While this paper performs well on dataset like PA and CAD, it performs can drop in more extreme or unseen environments as slow light or weather challenge scenarios. For this future work, we'll explore integrating multimodal sensors, like combining with LiDAR or radar will make the model more efficient and and it may make it suitable in various environmental conditions like low lighting or weather conditions. Next, static graph construction. The current graph structure is predefined and doesn't adapt in real time, which may limit its flexibility in rapidly changing scenes. For this, introducing a dynamic graph generation mechanism will allow the model to update its pedestrian interaction map on the fly, improving responsiveness to sudden movements or a change in pedestrian behavior. Next, limited context awareness beyond pedestrians. This paper mainly focused on pedestrian interaction and often overlooks contextual factors like nearby vehicles, road sign, or crosswalk signal. And by extending the external model will incorporate contextual scene features through a fusion model that considers a semantic maps or traffic signal data, improving decision making in traffic-rich environment. Next, no unnecessary uncertainty modeling and prediction. The current model gives a single deterministic output for pedestrian intention without estimating confidence. This can be risky in real-world systems. To overcome this, incorporating probabilistic models like Bayesian layers or dropout concerns can help estimate uncertainty, making the system more efficient. Conclusion. While this paper already performs impressively well, I see these limitations as chance to make it even better by focusing on improvements like dynamic graph updates, deeper scene understanding, and introducing uncertainty awareness. My goal is to create a model that's not just accurate but also more adaptable and trustworthy and safer. These enhancements could bring this much closer to being a real world solution for autonomous vehicles. Thank you.